All right. Today we will resume our discussion on the representation, on the restriction of a representation to a normal subgroup of index 2. Recall that for a finite group G with a subgroup H of having index 2, if for any irreducible representation of G, irreducible representation of G over C, then with character chi, so we can restrict the character to H. So the restriction of this chi is going to be the character of restriction of rho to H. So if chi is irreducible, we have already discussed that there are only two options for the restriction of chi. So option one is it is itself irreducible. Option two is sum of two distinct irreducible characters. So sum of two distinct irreducible characters, distinct irreducible characters. All right, so this is we just have only two options. Now we will show that we will deal with both the situations one by one. So first, let's go deal with the situation when restriction of chi is irreducible. So res chi is irreducible. This is the okay. So when we deal with restriction of chi, the irreducibility of restriction of chi, let us recall that whenever G has a subgroup H having index 2, then we have the following one-dimensional representation of G, which is given as follows: that for every H, this is 1, for every H in H, and -1 otherwise. Okay, so this is a representation of as a one-dimensional representation of G, and then we can multiply so we can consider this. This is also going to be a character of the representation lambda times rho. Okay. Also recall that chi is irreducible. If chi is irreducible, then that implies lambda chi is also irreducible. Lambda chi is also irreducible. And needless to say that the restriction of chi and the restriction of lambda chi both are same, right? I mean, once we restrict chi and lambda chi, if you restrict both of them on H, both of them to H, then what you get is the restricted characters are same. So the relevance of this lambda chi to the situation when the restricted character res chi is irreducible is the following: that we have in fact seen that in the last video. That is what it says, that the res chi is irreducible. Res chi is irreducible if and only if chi G is non-zero for some G, in G lying completely outside H, and then finally and then finally the second thing is chi, and so chi not equal to lambda chi. So this is what we have seen in the last video. So so therefore, in the situation when the restriction is irreducible, we have the restriction is irreducible, we have the following informations about chi. So the first information says that it cannot vanish identically outside H. The second information is chi, and lambda chi cannot be same. So we have these two information about chi. Okay, now we shall use them. So what we want to investigate is let's again see. So chi is an irreducible character of G. So is lambda chi. So this is also irreducible character of G, and the restriction of both chi and lambda chi are same. Okay. So the natural question is: are there any irreducible character? Are there any irreducible character of G such that whose restriction to H coincides with the restriction of chi? So let me repeat. So basically, can we have, so given a chi reducible character, we want to see which irreducible characters of G when they are restricted to H will be equal to the restriction of chi to H. Okay, so we already found one character lambda chi, that's when that is restricted to H, that exactly coincides with the restriction of chi to H. So whether there is any other or not, we will see why these questions, why this question is very important, that whether there is any other character whose restriction to H coincides with the restriction of chi or not. We will see shortly when we will when we will come to the character table of H from the character table of G. Okay, first let's see that. So let phi be an irreducible character of G. Let phi be an irreducible character of G, such that restriction of phi to H is same as the restriction of chi to H. Okay. For example, lambda chi is a choice for such a phi. If this happens, then what can we see? So let's see that. What about chi plus lambda chi? So when G belongs to H, then both of them are basically chi G. So therefore the sum is 2 chi G when G belongs to H. When G doesn't belong to H, then this is chi G, this is minus chi G, so the sum has to be 0. Okay. So this is what we have. Now what we will consider, we will compute the inner product of so inner product of this with chi. So the inner product of this with chi, so according to the definition, this is just nothing but, so G is in G, so the value of this at the point G, right? And for that we know that if G is outside H, then that vanishes. So therefore the inner product just turns out to be 2 times chi G times phi G prime. Okay, because when G doesn't belong to G, this just vanishes. Now we use that what is 2 by order of G. We know that order of G by order of H is 2. So therefore 2 by order of G is nothing but 1 by order of H. So then I will just change the index. So this H belongs to H, chi h and phi h bar. Okay, phi h bar. So now what is this? Isn't this just the restriction of chi to h and the restriction of phi to h, right? Now assume now as I have said that our according to our other assumption, this is irreducible and this equals to this. So therefore res phi to h is also irreducible, and this is in fact equal to res phi of chi, res h to of chi. So therefore what is this? This is just 1. Okay, so that's what we have. The compute is this fellow is 1. Okay, and that really tells us a lot, because both these are irreducible, distinct irreducible characters. They are distinct because we have assumed that this is irreducible. Therefore these two characters are distinct, and this is also an irreducible character according to our choice. So therefore here you have a sum of two irreducible characters, another irreducible character, in inner product is 1. So what does that mean? Doesn't that imply that phi is either chi or lambda chi, right? So thus we have seen that this phenomenon, that starting with an irreducible character phi, starting with the irreducible character chi, whose restriction to h is also irreducible. Then apart from chi, this is the only lambda chi is the only character which can coincide to the restriction of chi when it is restricted to h. This is the only choice. Okay, that is what we have seen. So thus when res chi is irreducible, then only lambda chi is an alternative, in the sense that when it is restricted to h, that gives that coincides with lambda chi, that coincides with the restriction of chi and nothing else. Okay, so this is what we get in this situation when this is irreducible. Now let's go forward, go for the situation when this is the sum of two irreducible characters. We will see, as I said, that we will shortly see why it is very important to have this, that is, apart from chi or lambda chi, nothing else coincides with the restriction of chi when it is restricted to h. Okay, so this is in the situation. We shall go for the next situation when this res chi is the sum of two irreducible. This is the when res chi is just the is not irreducible, so hence it has to be sum of two distinct characters of h, where psi 1 psi 2 are distinct irreducible characters of irreducible characters of h. Okay, so this is the situation we will deal with right now. And you see this again, recall that if chi is not irreducible, res chi is not irreducible, then that is equivalent to say that so chi vanishes identically, outside h. Chi vanishes identically outside h. Okay, so and then of course in this case chi becomes equals to lambda chi. So here at least this one is not going to be of much help to us. So we will rather forget them. This is what is crucial for us. Now let phi be another irreducible character of G, such that such that res phi to h is all coincides with res chi. So basically two irreducible characters, when they are restricted to h, they become equal. Okay. Now if that happens, let's see what we can say about this chi and phi. They are I want to see what happens to their inner product. So first of all, what we have to see is the inner product that exactly becomes, according to our definition, chi g times phi g bar. Okay, chi g times phi g bar, and chi vanishes identically outside h. So therefore this just boils down to the situation that let's say chi h phi h bar h is in h, right? So now in order to bring it in the form of what we do is we'll divide. Well, let's do it in this way: half 1 by order of h, because order of g by order of h is 2, so therefore 1 by order of g is uh, half order of h, right? So then this is just this is just this uh, phi h bar. So what is that actually? It is just the inner product of res chi h with res chi with res phi this. Okay. Now so according to our definition, this is psi 1 plus psi 2. So then what we have, psi 1 res h phi plus half psi 2 res h phi. Okay, and remember that both these are distinct irreducible characters of h. Okay, so from here, if you now see, so what we get is this equals to this equals to this. Well, let me just, okay, so what we have got is this equals to this. Okay, so what does that show? So suppose so if this is 0, then certainly both of them have to be 0, right? Because the inner product of two characters is always a non-negative integer. So if this is 0, then this in both the terms are 0, and if one of the term is non-zero, then this has to be 1, and this has to be non-zero. If one of them is non-zero, then this will be non-zero. Since both of them are irreducible characters of G, so once they are non-zero, that means chi has to be equal to phi. So what this shows us is the following, that if one of this term is non-zero, so what do you mean by one of this term is non-zero? Remember that this is a representation of H, this is a representation of H, this is from a representation of H, and this is an irreducible character. So either this is non-zero, that is non-zero, that means that the representation corresponding to the irreducible representation corresponding to chi I belongs to the restriction of the representation corresponding to phi. Okay, so thus what we got is the following, that if this phi whose restriction to h coincides with that of chi, so what shows that well, so yeah, let's introduce a terminology that will help us to talk more, that will help us to yeah. So we're going to introduce a terminology here. So with the in this terminology, it will be more, it will be easier for us to talk. So uh, suppose for I mean it's a general definition that suppose shy is a character of shy is some character of H, not necessarily reducible character of H, and let say theta be an irreducible character of H. If psi, the inner product of psi and theta is non-zero, then what it means is when we write psi in terms of the irreducible characters of H, then because since it's a character of H, it's a class function, so it will be the linear combination of the irreducible characters of H. So this condition just ensures that in that expression of chi as a linear combination of the irreducible characters of H, in that combination the coefficient of theta is non-zero, right? So in that case, we would say theta is a constituent, constituent of phi. Yeah, I think you are able to realize that why it is reasonable to call it a constituent, because in the expression of phi, you can as a linear combination of the irreducible characters. Once you ignore the zero, the characters whose coefficients are zero, then you are just left with those who are coefficients are non-zero, and their sum, their sum becomes equals to phi. So they, in a sense, those characters constitute psi. So therefore, that is what it is legitimate to call them as a constituent. So once we have this terminology in our hand, let us just formulate the above observation in the following way: that if theta is an irreducible representation of G whose restriction to H coincides with that of chi, then if uh, one of the if one of the if at least one of the constituents of res chi is also a constituent of res phi, then phi has to be identical equal to chi. That is what we have seen. If so, in other words, if res chi and res phi, they have at least one constituent in common. If they have at least one constituent in common, then they have to be equal. So we'll just write it res chi and res phi res chi and res phi. Recall that res phi is also like this, since phi is also an irreducible character, so even for this we have two options. So either it is itself irreducible, or it has two distinct irreducible constituents. So if they have any irreducible constituent, in fact we should remove the word irreducible while saying irreducible constituent, because constituents are defined as the irreducible ones. So if they have any constituent in common, okay, any irreducible character, irreducible representation that that is contained in both of them, then well we should remember that uh, if I mean if an irreducible representation is contained in both into I mean suppose we have two representations of a finite group, and we have another irreducible representation that lies in both that is contained in both of them, then in that case we say that the representations are not disjoint. Okay, then we say the representations are not disjoint. So in this language here, what we see is if they are not disjoint, again, being disjoint means there is no constituent in common. They are not disjoint, then chi has to be equal to phi. Okay. So in the situation when the restriction is not irreducible, then for anything else, then for any other restriction whose uh, then for any other restriction uh, sorry, yeah, then for any other restriction are not disjoint. Just a minute. No, no. According to our assumption, we sorry. We have just made slight mistake that this condition won't happen. So this condition won't happen. Sorry. So let me just again repeat from the beginning. This chi is an irreducible representation of G such that the restriction is not irreducible. Let this phi 1, phi 2, and then it has to be the then it has to have two distinct constituents. Let's label them as psi 1 and psi 2. Psi 1 and psi 2. Then for any irreducible representation of phi whose restriction to H, like then we consider any irreducible representation of representation phi of G, which has we consider any representation phi of G, and then we restrict that to H. We restrict that to H. We restrict that to H. Then what we say that if this restriction of phi is disjoint from is if this is not disjoint, from restriction of chi, then phi has to be equal to chi. Okay. So sorry, this condition that this is equals to this is equals to the restriction of chi to H, that condition certainly does not make any sense to what we are doing. So here let me just again repeat for your convenience that we started with a irreducible character of G whose restriction is not irreducible, hence the sum of two irreducible characters. And then we, for any phi and any irreducible character phi of G, if this contains phi 1 or phi 2, if this has psi 1 or psi 2 as one of its constituents, then if again try to understand that we don't we do not bother whether here a priori we do not bother whether the restriction is identically equal to the restriction of chi. Here what we are investigating is, here we are concerned about whether this has at least psi 1 or psi 2 in common with restriction of chi. If this is so, then phi has to be identically equal to chi on G. Okay. So thus we have dealt with both the situations. We will now quickly summarize and finish. So what do we have? We have the following thing. First of all, whenever G is a subgroup of H, not necessarily normal, then we know that every irreducible character of H is a constituent of some is the constituent of the restriction of some irreducible character of G. Okay, that's what we have seen earlier. So thus all irreducible characters of H can be found in the restrictions of the irreducible characters of G. This is what the first point says, that how to find, where to find all irreducible characters of H. It says that they certainly occur in the restrictions of the irreducible characters of G. This is second observation is Suppose in addition that H has index 2, suppose in addition that the subgroup H has index 2, okay, then uh, we have two possibilities, that we start with the irreducible character G of irreducible character chi of G. So when the index is 2, then we have two possibilities. So we start with an irreducible character chi of G. If it happens that chi vanishes identically on the complement of H, then once we restrict chi to H, well, sorry, if yeah. So just a minute, let's just quickly review. Yeah. So if yeah, so if chi does not vanish identically on the complement of H, then certainly this has to be a irreducible character of H. Then there has to be a irreducible character of H. Okay. And furthermore, yeah, and furthermore, uh, if we restrict some other, if we restrict some other character, some other irreducible character of G to H, then that has to be that will be different from this. Okay. So thus, what I mean is the following: uh, all the characters which do not vanish, all the distinct characters of G which do not vanish identically outside H, once we restrict them to H, we will get exactly those many irreducible characters of H. Clear? I repeat. So this just shows that in the all the characters which do not vanish identically outside H, so once we restrict them to H, then we get irreducible characters of H, and furthermore they are different. Okay, so this gives us a few distinct characters of H, namely but the restriction of the characters from H which do not vanish identically outside 0. So this is in this way we get some characters of some irreducible characters of H. And the third thing is that if chi vanishes identically outside H, then once we restrict chi to H, then for the from the restriction I will get two irreducible characters of H. And furthermore, if we restrict a different different character of this kind to H, then the constituents that we are going to get for that character are not going to they will not be equal to any of these. So thus, let me put it in this way: for each character of this kind, when we restrict them to H, I will get a pair of irreducible representations of H, and distinct such characters give us completely distinct pairs. That is, completely distinct means none of the like A comma B is completely different from C comma D. By that, what we mean is neither A is equal to C nor B is equal to D. So distinct such chi's always give us completely different pairs of irreducible characters of H. So now this is what the scenario we have. First of all, we know that every character of H should be every character of H will be obtained by will be obtained in the restriction of irreducible characters of G. This is what we know in the very generality. So keeping that in mind, in the very special situation when H has index 2, now in that very special situation, as we know that, as from 1, as we know that all the characters, irreducible characters of H will be obtained in the restriction or in the restrictions of the irreducible characters of G. So with this one in mind, in this very special situation, when we start restricting the irreducible characters, we first divide them into two classes. In class 1, we have the characters which do not vanish identically outside G. So for this class of characters, once we restrict them, they are going to be reducible characters of H, and they will be distinct. So distinct chi's will yield distinct irreducible characters or of H. And the second class, that is where the characters vanish identically on H. So for all these characters, when we restrict them, we get two irreducible characters of H, and the two characters that are coming from the restriction of chi are not going to be obtained are not going to be obtained otherwise, in the sense that these two characters that we get from the restriction of chi, we won't find them if we restrict another different character in the second class to H. Okay, so thus we have an idea that how to find the irreducible characters of H when H is index 2. In the for the first group, it is the situation is in fact perhaps the most ideal one. But in the second case, it is slightly non-trivial, because after the restriction, you have to split them as a sum of two irreducible characters of H. But in practice, what happens that the first situation occurs more often than the second one. So in most good examples, the first situation almost suffices everything. So like then in that case, we can easily find the characters of H, irreducible characters of H, without much difficulty. But in the other case, we need some extra work to do. So however, it is quite clear that the characters obtained from the first class of characters of G, and the second class of characters the characters, irreducible characters of H, that we obtain from the first class and the second class by restricting them, are all the irreducible characters of H. Okay, so in the next video, what we do is we will so whatever we have seen in the last video and in this video, we will apply them to a concrete situation, namely when G is S5 and H is A5, because this the most standard example of an index 2 subgroup is alternating subgroup of symmetric groups. So the theory that we see here, that we have discussed in the last two videos, I mean, they must apply to Sn and Ans. Okay, so for any Sn and any N, this theory will apply, that which we have discussed. But you see, but the difficulty is that what we have just said there, in that we have seen that from the irreducible characters of G, we get how to get irreducible characters of H, I mean, as much as we can. But this certainly does not help us if we do not know the irreducible characters of Sn. So therefore, I mean, in order to apply this technique to, to apply this theory to get the character table for an, we must have the character table for Sn. We must have that in our hand. When n is so unfortunately when n is getting large, then we don't have that. But fortunately for S5, we know all the characters, which we will be seeing in the next video. And then once, since we know the character table of S5, we know the universal characters of S5. From that, using what we have done in this video and the earlier video, we apply them to get the character table for A5. Okay, with that I will finish.